Hi everyone, so my name is Tom Cronin. I'm the head of data science at Lloyds Banking Group. Me and one of my data scientists, Tola, are going to talk you through responsible AI and delivering data science safely at scale. I think following on from the keynotes, this seems to be a much more of an apt topic than we thought it was going to be, so I feel like we've been somewhat put on the spot. But I'm going to get started with this date. What does this date mean to anyone? Anyone recognize this date? It should do, right? It should make a lot of sense to people. Maybe this picture will help. So, one of the stranger things about presenting about Lloyds in the US is actually in the UK, every single person has heard of Lloyds Banking Group. It's a pretty well-known. Everybody knows what Lloyds Banking Group is. In the US, a lot less so. So, I like to set the context, and there was a fellow called Sampson Lloyd II, born in 1699, who founded Lloyds Banking Group in 1765. So Lloyds Banking Group is older than the United States of America. It's older than the Australian colonies. So we have quite a long history, and actually parts of Lloyds Banking Group, the Bank of Scotland goes back even further to, I think, to 1686. So an almost unfathomable history of banking. So I guess for anyone who doesn't know who are we? This is my only kind of corporate slide I have. We are arguably the most well-known UK banking institution. Around a third of the UK has some kind of retail banking relationship with us, whether that's a checking account, a mortgage, credit card, et cetera, and we trade across a number of household brands. And we have a very distinct, I guess, kind of value policy, and what we're all about is being the quote-unquote best bank for customers. We're all about creating that good customer experience and helping Britain prosper. And so kind of back to that point on the sort of historical nature of Lloyds, we've had a long and rich history of innovation. So there's a lot of stuff on this page. So at the top left is one of the oldest branches in the world. I believe it's in part of Norwich. It's now a Subway store, so a little bit of a, not quite the glorious end it deserved, some might say. At the bottom left, one of the world's first ever telephone banking services and exchanges. The thing at the top in the middle, I'm not 100% sure what it is, but it's some kind of printing press. So back in the 1800s or 1900s, whenever that was, that would have been groundbreaking. And the most interesting thing and real forgotten relic of history is at the bottom in the middle, and it's quite hard to tell what's going on, but essentially this is someone doing the world's first version of internet banking, and they're using teletext, and there's a telephone on the floor that's basically listening to a microphone, or like a microphone is talking to the telephone, and it would have just been screeching this total nonsense, and then on the TV your bank balance would have appeared. And for some reason we thought that was a great idea in the 80s. But we've come a long way since then, through to putting through the world's first kind of cash points, and the world's first ever banknote is at the top right. The first ever time someone wrote on a piece of paper, "You must pay me this much money." So within Lloyds Banking Group is enormous, so we have about 70,000 colleagues, and so specifically myself and Tola come from a part of Lloyds that we call Group Transformation. So we are set up as a centralized applied science, data science function, and our role is to drive data science change and the kind of culture of modeling and data science across a very large organization. I'm sure many of you have come from, some of you may have come from financial services, and a lot of the messages that we heard this morning pretty resonated quite strongly of, you must drive that model culture. That is 100% something I was aggressively nodding to, and that's essentially what my role is all about. So just to set a bit of context, we kind of deliver things in three main labs. So we have what we call our virtual assistance lab. So this is essentially a bunch of cognitive services. So anything like, I don't know, chatbots through IBM Watson, through to, I don't know, anything that kind of represents an interaction with a customer that has some kind of AI lens to it. We have our robotic process automation lab. So this is like, it's relatively boilerplate stuff. It's in a lot of ways not that exciting, but it's all about trying to take a lot of the really painful stuff out of a lot of people's jobs. We've got a lot of old heritage systems that require an agent to copy paste across screens. Madness. No one wants to do that. You can set up some pretty basic robotic software to do that. And finally, the best part, because it's the bit I'm from, is the data science and machine learning lab. So where we sit is anything that's not related to cognitive or robotics is essentially our problem to try and solve. So this means that we operate across both the retail bank, the commercial business, so like business-to-business lending, and the insurance business. And our job is to drive value through data science and machine learning products. So for example, the group, as all financial services and insurance companies have had models for longer than I've been alive, but there are a lot of areas of the business that just don't have this kind of modeling way of thinking. If they're lucky, they're a data-driven function that looks backwards. Our job is to turn them into a predictive function that looks forward. So rather than thinking, this many customers had a bad outcome, what can we do about it? We should be saying, we think this customer is going to have a bad outcome. Let's do something about it now so it never happens. And so kind of the main sort of topic that we're going to cover today is around responsible AI. Responsible AI is a bit of a, I guess, a sort of buzzword at the moment. But I suppose I just wanted to talk a little bit about what it means for myself. So to give a sense of scale, so our data science team has about 50 permanent colleagues and another sort of 40 or so contractors and consultants. So we're quite a large team. And we're getting to the point now where a lot of our models are starting to have some real material impact. And it was very interesting listening to the Netflix talk around democratization, and everyone can have access to the data. And my financial services brain was melting. I was like, oh my God, I can't even describe how hard this would be. Like, I'd love to live in this world. But taking aside the kind of standards around data controls and data-related stuff, a big question's emerging on how do you responsibly use models, and when is it appropriate to use a model to predict something versus letting a human do. And I certainly am not going to try and outdo some of the amazing speakers this morning, but I'm just going to share kind of, I suppose, my thoughts on where we're going with this as an organization. So most of this is driven out of, I guess, a couple of key risks. So in financial services, one of the most important things that we need to be able to do is explain why we made a decision. So for example, if a customer feels like we've unfairly, I don't know, let's say they've applied for a mortgage and they feel like they were rejected maybe because of their geodemographic background, we as an organization need to be able to say, whoa, hang on, no, we treated you fairly, and let us explain how we treated you fairly. But equally, if a customer says, hey, hang on, why was my card blocked for fraud? Then there's a question of like, well, hang on, if we explain all the nitty-gritty of the fraud rules, you could backwards engineer that and commit fraud against other customers. So where do we draw the line on when is it responsible? Because full transparency, I don't think, is the answer. Unfortunately, there's too many evil people in the world to let that happen. So in terms of responsible AI, we've kind of broken it down into three main areas. My slide's rubbish. There we go. So there's three main areas. So we've got data ethics and fair models. So this is all about, I guess, fairly boilerplate stuff on data ethics and data control. So for anyone who's not aware, in the EU, there's an exciting new regulation called GDPR, which basically means that life is really difficult all the time. But ultimately, I missed off a thing. Ultimately, as a customer, it's great. And as a human being that also interacts with other businesses, it's great because I now have a lot of rights that I can go to any organization and say, how are you using my data? And I want you to explain how you've used models to influence me and provide me with services. So there's a lot of stuff that is regulatory and we must do, but equally, there are the much more gray areas of things like in credit scoring. If your model accepts more women than men or more men than women, you can look at that and say, okay, well, maybe it's just the status quo. Maybe it's fine. Maybe it's the status quo. But then you could argue, actually, is it our responsibility, because our bank's all about helping Britain prosper, to try and fix the status quo and move towards a more fair state? Or a purist mathematician might say, force it to be 50-50. But is that really fair? Don't know. It's a huge ethical conundrum, and it's certainly not something that we're trying to solve by ourselves. The second part is all around explainable AI. So this is what I won't spend much time on this. This is what Tola is going to go through in a couple of minutes. But it's essentially, it's trying to balance out the worlds of a beautiful linear regression model that I 100% understand what's going on. I could tell the customer exactly why I made this decision, but it's kind of a bit old hat now, and there's a lot more exciting methods that can drive a lot more statistical value. And finally, the thing that a lot of people don't care about, but it really is the most important thing, is around defining your what I would call the data science lifecycle and your governance processes. So how can you make sure that as you deliver things on a sort of like groundbreaking scale? So for example, for context, the Lloyds has a model that manages the capital provisioning risk of our mortgage book. And we have about somewhere to more than a third of the UK's mortgages. So if that model explodes, and we put some highly risky model in, it explodes, say goodbye to the UK economy and bad news for the rest of the world because it will probably bring down everyone else. So that is a great example of when, you know what, we probably want to stick with some relatively safe old school modeling methodologies. But when you're looking into the world of fraud prediction, the whole point of fraud prediction is you have to be able to quickly react, and you've got to beat the competition who are trying to undo you at every step. So how do you balance these two things? And the way we do it is through a kind of embedded way of working, making sure that documentation isn't an afterthought. You document as you go through a defined process. And I'm very excited that, and this isn't a paid promotion, I'm very excited that Domino is going to help us do that. I'm looking forward to that because right now it's very painful. You have to sit down and write a huge Word document at the end of a project. And frankly, no one wants to do that, but we all accept that it's required. So I think that's the end of my little bit. So I'm going to hand over now to Tola, who's going to talk us through a bit more detail on explainable AI and the sort of areas that we're starting to look at.
Cool, thank you. Forward, great. Can everyone hear me okay? Awesome. I'm just going to pace up and down here, so don't be distracted by that. Hi, my name's Tola. I work as a data scientist at Lloyds Banking Group, and today I am here to talk to you about explainable AI, which I will mostly refer to as XAI in this session, so I hope that's okay. So, I believe it's fair to say AI has grown significantly over the last few years with more and more organizations deploying AI models to basically augment and replace human making decisions. And also, when I talk about AI models, majority of us are familiar with quite a lot of this popular AI products, such as the likes of Siri, Alexa, Google Home. But from a traditional perspective, for example, Lloyds Banking Group, we've got AI models that basically would predict whether a customer's credit application should be approved or not. But within the healthcare services, you could have a model which predicts whether a tumor is cancerous or not. And in some of these scenarios, it's becoming increasingly important to provide explanations on how some of these decisions are being generated. And this is actually due to increased pressure from customers, but also, like Tom mentioned earlier, this is becoming increasingly important due to changes in regulatory requirement, famous GDPR. We all love it. So, what is XAI? In very simple terms, XAI is basically the ability to explain an individual model's prediction. So to bring this to life a bit, imagine if you feed in a bunch of characteristics about a customer into a Blackbox model, which has been trained to basically tell you whether or not to approve a customer's loan application. And as an end user, you get this result saying, yeah, this customer is all good, approve the loan. For an end user, this is quite confusing, as there's been no reasoning whatsoever provided as to why this customer is a good customer and basically I should approve the loan application. And this is where XAI comes into play, because for an end user, this could lead to mistrust in the model, and most importantly, it could actually lead to bad decisions being made in the model. Bad decisions being made based on the output of your model. And this is one of the problems that XAI is actually trying to solve. But another area where XAI is actually pretty decent is it could actually be used as a debugging tool and identifying bias in your model. And I absolutely love using this example. Put your hand up if you read the line paper. Oh, great. Oh, just one person. That's fine. That's great. So, looking back at the line paper, I'd definitely recommend it. It's a great read. They basically built a classifier to identify an animal in an image to be whether a wolf or a husky, right? And this is an example of some of the images that was fed into the classifier and some of the predicted outcome. However, after further investigation into this classifier, they realized that one of the key drivers of this classifier predicting a wolf is actually snow in the background. So basically, they built an awesome snow detector, which obviously wasn't what they were trying to do, so this is complete garbage. But, like we said earlier, this is massive. It's so big, it is ridiculous. I mean, in the UK, when this kicked in, every single organization was just having a field day. I mean, even as a customer, you were having at least 10 emails a day from various organizations, just basically trying to get your consent to keep your data. And some organizations are thinking, when the hell did I sign up to this? And you're like, no, I'm out. So this is actually really big for us. That is actually by law, in some cases, not in all cases, customers do have the right to basically request an explanation on how we've made certain decisions on them. But finally, I think XAI is actually here to demystify machine learning as a whole and basically make it a lot more transparent and basically increase trust in machine learning models. So going back to the previous example where I said you feed in a bunch of characteristics into your black box model and you get an output. To make this better, obviously that's some of the features, but imagine if alongside the predicted output from the model, you get some form of explanation on how, even though this is a black box model, but for a specific customer, you get some sort of explanation as to how each feature's contributed towards the predicted output, and also whether the feature's got a negative or a positive impact. This is great, especially for an end user, because then if I look at it as an end user and I'm like, yeah, that pretty much makes sense to me. By default, that just helps you increase trust in your black box model, which is basically where we're trying to get to, or at least where all the development in this space is trying to get to. Until recently, organizations have had to pick, in some cases, between your white box models and your black box models, where your white box models are your likes of your good old linear regression, decision tree, or your simple naive Bayes, because they're very, very easy to interpret. However, in some cases, I really, really need to iterate this. In some cases, not in all cases, there's only so much predictive power that can be extracted from them in comparison to your black box models, which are your likes of your ensemble models, bagging, neural network, where sometimes you can actually extract more predictive power from them. But this isn't always the case, because you will be surprised to find out that if you've got a very well formulated data science problem with very informative decisions, sometimes going with a black box model doesn't actually give you a statistically significantly better performance in comparison to just going to a white box model. And this is very true, but by default, some people just think, I need to build a neural network to solve my problem, and I'm just going to get an awesome performance. That's not always true. But with the developments that's happening within the XAI space, I believe this whole interpretability performance trade-off will soon become a thing of the past. And speaking about developments that's happening in this space, there's actually been some XAI libraries that have been written and are available open source. I will talk about the first three very briefly in a bit, but you've got your likes of Lime, Anchor, Shap, Eli5, which stands for Explain Icon 5. You've got Skater, and you've got Scalar and Expert Sys. I need to get my words right. Which is basically an sklearn wrapper for Bayesian rule-less classifier. So let's go into a bit more detail about Lime. Lime basically stands for Local Interpretable Model Agnostic Explanations. When model agnostic basically means it doesn't make any assumption about the fitted model. And in very simple terms, how does line work? So imagine if you've got a decision boundary that is the boundary that basically separates a positive from your negative class. And I'm trying to explain this specific instance. The way line goes about it is it generates synthetic data set around the instance to be explained, but then weights it based on similarities to the instance to be explained, and does a very, very simple thing. That is, just fit a linear model locally, which is great, because then from this local fit, we get some coefficients which we can then use to interpret what's happened locally and why that model predicts such an outcome. But based on what I've just said very quickly, I'm sure some of you are thinking that has got some major faults to it, because it makes this strong assumption about a linear fit locally, but also in terms of generating this synthetic data set around the instance to be explained, there is some element of randomness in that as well, which obviously isn't great. But you could have cases where you create an explanation using line for a specific instance, and it tells you feature X has got a positive impact on the prediction. And then you create another explanation for another instance, but then it tells you that same feature has got the opposite impact. So as an end user, this is quite confusing, because then you don't really have a good understanding of the coverage. That is, when the specific explanation actually apply. And this is what the guys that implemented line realized. So they thought, hey, back to the drawing board. Let's come up with Anchor. Anchor is basically another model agnostic method, which is based on if and then rules. Very, very simple. And what they've tried to achieve with this is to have much of a better coverage in terms of explanations that come out of Anchor. And what they pride themselves with Anchor actually is very easy to understand, and also, based on some user study, they realize that actually, with Anchor explanations, it's got a high human precision. That is, humans are likely to predict the outcome of a model correctly quite often. So I've just got some examples of some anchors, which is basically some conditions that's been learned by the anchor model from 3 different data sets. You've got the adult data set, which I think quite a lot of data scientists know about or played around with at some point in your data science career. You've got the LCDV data set and the lending data set. So I'm just going to use the middle one. Oops, nope. Let's go back. That. So I'm just going to use this as an example, because we touched on this very briefly where we were talking about identifying bias in your data. So looking at the anchor, the second anchor from the LCDV data set, which basically tells you that if for a specific individual, if that individual is male, is black, he's got 1 to 5 priors, not married, and has committed crime not against property, then that individual is more likely to be rearrested. Very quickly, you pretty much identify that there's something wrong with your model, but then again, it depends on how ethical you're trying to be with your model, but that's a whole different conversation on its own. But that is basically how Anchor works, in very simple terms. Every single condition has to hold for this anchor to basically say, okay, for this specific instance, I believe this will be the predicted output. Because if only 3 of the conditions hold, then that wouldn't hold at all. And the final method, which is actually the most popular, everyone seems to love it, is SHAP. SHAP stands for Shapley Additive Explanations. And this is actually a concept from game theory, where Shapley values are basically calculated to identify how much reward each player in a collaborative game should receive. So taking that concept and applying it to machine learning, half of you are about to hate me very quickly, but please don't let that give you a headache. So taking this concept and applying it to machine learning is basically, I need to calculate the Shapley value for each feature that is contributed to us predicting a specific outcome for a specific instance. But the way it works is, to calculate how much a feature is contributed to as a specific prediction, you have to think, okay, what would my model predict with and without this feature? But if you were to look at the prediction with a specific feature, this is dependent on every other feature that's been fed into the model. Hence, oops, I'll come back to this. Hence this weird, complicated equation that I kind of felt the pressure to put into because, hey, it's a data science conference. It needs a formula somewhere. But basically, this is just basically summing over every single combination of the predicted outcome with the feature that we're in question, and without the feature in question and being weighted by some sort of factor. But to bring this to life a bit, imagine if you've got a classifier which predicts whether a specific patient is diabetic or not. And to make this very, very simple, you only feed in 4 features into this model. But we're basically trying to calculate the Shapley value for a smoker feature, that is, how much does the smoking feature contribute towards the predicted outcome for this specific patient. Talking about summing over different combinations of all the features that goes into the model, I've kind of broken this down into all the different combinations. But you have to basically take these combinations and then think about, okay, what would my predicted outcome be with and without the smoker feature? And then you sum over all the combinations, multiply it by your weighted factor, and then you get your Shapley value. I really hope that makes sense. But that's me trying to simplify SHAP the best way I can. But to bring it to life a bit, I'm going to demo what you could do with SHAP in a commercial sense, and some of the Shapley plots are really cool and very, very useful, using a transportation data set and basically working with a random forest classifier, because obviously that's one of the most popular black box models out there, and basically how we can get some explanations from it. Sorry. Awesome. Yeah. Great. So like I said, we're going to look at some transportation data set, which I've loaded. This has all been preloaded just so it all goes smoothly and nothing fails epically. So this is just a transportation data set where you've got some information about a specific household and also what mode of transportation they use on a specific day. We can see very quickly that this is a multi-class problem, but just for this demo, I decided to simplify it to a binary problem to say, okay, can we predict whether a specific household is going to drive on a given day or they choose not to? You do your typical data pre-processing, do your training test split, one-hand coding my categorical features. This is very boring bit, so I'm going to skip through it quite quickly. And then fit to a basic random forest classifier. I'm not saying in any way that this is the optimal hyperparameters, just getting something up there for show. And what's great about random forest is it's got some form of like global interpretability, which is good, but in some cases that isn't good enough. Because here we can see that actually the distance feature is an important feature, but for a specific instance, we don't actually know how that feature is contributing towards the predicted outcome. And this is where SHAP comes into play. So I've loaded my SHAP, got my import SHAP. I'm looking at a SHAP tree explainer because obviously the fitted model is tree-based, random forest that bin. And what's great about SHAP actually is you can get some form of global importance from this as well, which I think is really, really cool and much better than the sklearn feature importance from the random forest. Because here, the little tiny dots is basically represents a specific instance for my test set, and the bottom axis is the Shapley value that is being calculated for that specific instance, for that specific feature, which is on your y-axis. So we can see very quickly that every single individual that hasn't got a license is less likely to drive, which is here. That is the feature where the license is no. If they've got a high value, this is a categorical feature. So for everyone that's got a value of 1, they've got a negative Shapley value. That is they're less likely to drive. And this is basically the Shapley version of global importance. But to look at explanations for a specific instance, so let's take an instance where the model's correctly predicted what an individual is going to do on a given day, and we're trying to understand what's driving that specific prediction. There's this plot in SHAP called force plot, which basically tells you the magnitude and the direction of the Shapley value for each feature. So here we can see that for this specific instance, we predicted a positive class for this individual, but then what's driving that prediction, and we can see distance is a big driver because obviously of the size of it, but it's driving it in the positive direction. Obviously, it's pushing it more towards the right hand end of the scale, and also the temperature as well. However, the age and the number of cars is trying to push it in the opposite direction, but with very, very small magnitude in comparison to the other features. But another thing that's great about SHAP is you can use this to interrogate where the model got it wrong. Here, the model's predicted a positive class, but actually, the individual did not drive on a specific day, but then you want to understand why the model thought this specific individual was going to drive on a given day. And we can see the distance is the biggest driver in this case as well. And the fact that it was on a weekend, and the fact that this individual actually holds a license. And looking at this as a normal human being, I would also expect the specific individual to drive on a given day, but for whatever reason, due to some form of manual intervention or whatever reason that we don't know, they decided to go another way. But there are other plots that you can get from SHAP as well. I do like the partial dependency plots, where you can pretty much see how two of your features interact with each other. I really like that. I prefer that to the Escalon version, but that's just me. But I will strongly recommend having a read through the SHAP paper. It is still very immature, I need to say. All these methods, all these techniques, that is being developed, they are very immature. If you look at the SHAP, PyPy page, in January they had some ridiculous number of releases, and when I couldn't keep up, so I just kind of stopped. But it's really interesting and it's really, really exciting. And like I said, strongly recommend reading the SHAP paper. And to bring this back to life and back to what we're doing in the team, explainability is a big theme for us. And like Tom said earlier, Lloyds Banking Group is all about doing the right thing for the customer and basically being able to help the customer wherever we can. And this is another reason why, if we're going to use models to make decisions on our customers, we need to be ready, in most cases, not in all cases, to provide our customers an explanation and basically help them to get better. And that's me. Thank you.
Are we done? Do we have question time? I don't know.
Oh, questions? Yes, sorry, I
don't
forgot.
I don't know how it works.
Hi.
The SHAP feature, right? So you used a random forest model, and
Yeah.
then you used SHAP. So
Yeah.
if you are developing like a neural net or something which is not tree-based, would the
There are various kernels in SHAP that you can use. So, for example, if you want to explain a neural network, for example, there's a kernel for that. So that was why, sorry, I didn't go into too much detail about it. So you can pretty much use SHAP for whatever black box models that you need explanation for.
right?
Yeah, you just need to change your kernel type.
Okay. So it is.
Sorry, your explainer type.
Okay. So I can use SHAP for tree-based as well as neural nets.
Yes.
Okay, great. Thank you.
But in some cases, this is another thing that we need to iterate, because all these techniques are trying to provide an explanation to a problem that you solved using a very, very complex model. And in some cases, you kind of have to be cautious about that, because these problems are complex for a reason, and Lime is trying to simplify that problem for you to get some explanation, and SHAP is also doing the same thing. So in some cases, your explanations might not be as good as you want it to be, but then again, there's a big question out there as to how do you define a good explanation. That's still something a lot of people are looking into. The anchor guys think a good explanation is one that's got high human precision, but then that's open for debate. Hi.
One of the things that's useful for a prediction is for regulators to be able to regulate a model or the model results. How close are things like SHAP to being able to help or to getting regulators to accept more complex models?
Like I touched on earlier, it's all about if you can provide some sort of transparency into your model, that is a good step forward in the right direction. And it's all about making your black box models a lot more transparent, because this are the type of models that terrify regulators, because you're just saying, oh, there's just loads and loads of complex stuff happening, it's just churning numbers and giving out something. However, they do have the right to question you to say, how do you know these explanations actually hold? How do you know they always hold? But that you don't know. And like I said, this is still a very, very immature field, and there's still loads of research happening in there.
So just to build on that, I've given a version of this presentation to the FCA, like UK major regulator, and essentially the FCA has a similar roadmap that says, how do we solve these problems? And everyone is shrugging. So it's like an open thing for debate at the moment. But essentially the regulators are saying, we don't know what the answer is, but you must prove to us that you're being safe, but we can't help you. So we're trying to figure it out ourselves.
So maybe a question for Tom. How did the government bailout of Lloyds affect this whole trajectory of responsible AI and in the industry, not just at Lloyds, I guess, but in...
I mean, so I think if I had to, so for anyone who didn't know, in 2009, with the financial crisis, the government bought a 40% share in Lloyds Banking Group, and essentially at that point started a massive transformation in what our group was all about. In 2008, 2009, we were a bank based in, I think, over 100 countries with a huge amount of toxic debt. And essentially between 2009 and 2012, we focused very much on building that core safe bank in the middle, operates in the UK. We established all of these things, helping Britain prosper, customers, blah, blah, blah. But ultimately, that's what's led to the creation of this kind of central data science function. So we'd had credit risk models. Explainability was always important. But up until relatively recently, the group strategy has been safe. We must do everything as safely as is reasonable. What we're all about now is kind of like cracking that door open and saying, actually, you know what, some of everything Tola's just talked about, that doesn't sound inherently dangerous. So it's kind of like eking it out into the world. But again, because of the scale, you can understand why the regulators are nervous about it.
Okay. Tom, thank you very much for the categorization of 3 distinct steps. I like that very much. And Tola, is this demo of SHAP, do you have it like in a blog post or a GitHub I can look at?
More than happy to share it with the Domino guys. They do have it. So I can speak to Karina to share it. If not, I can share my GitHub handle.
We might be able to post it through the app or something crazy like that. But
yeah,
we'll figure out how to share it
Thank
in
you
a
so
sensible
much.
way.
Oh,
Yeah.
wow. Awesome. Cool.
One more? I mean, we're around anyway if you want to come talk to us. So.
Yeah, just grab us.
So it seems like most of your work around XAI is keeping the black box as a black box and seeing how adjusting the features, omitting features affects the eventual outcome.
Yep.
Do you guys at Lloyd do any work into actually opening the black box and introspecting it and interpreting maybe any of the inner workings and explaining maybe neurons or layers within some kind of network? Or is it mainly keeping it a black box?
I think at the moment it's mainly keeping it in the black box. And I think a lot of that is because of where we are in terms of our maturity. So for example, we're at the stage where we're migrating from using logistic regression to using random forest. And it's kind of back to this whole thing that we were talking about this morning on the simplest model that solves a solution is the best model to pick. Right now, for us, there's a lot of relatively low-hanging fruit in terms of using random forest to drive benefits. I think once you're getting into that kind of Keras framework type of model, actually people would be quite interested in these specific neurons, this layer. This is what seems to be introducing the complexity. Explain it, please. But frankly,
we're not there. And I think given the research space isn't there yet, most of the approach quite a lot of people are taking is model agnostic. That is, I've got a black box model, I've got some prediction. How can I understand what's happened inside that model without peeking into the model? Even though the way it's pitched is, hey, let's peek into the black box model.
Yeah.
but that isn't what most of the techniques out there do.
Okay, thanks.
But it'll be interesting to see what happens in the space and pretty much
Yeah.
how far it goes.
Cool. Thanks for coming, everyone.
Thanks, guys. Awesome.